And also please make sure that if your laptop is on the mute, that you are muted. All right, today we are going to be comparing what happens when you take any function f of x and you put a square root on top of it to make it square root f of x. I want you to think of this as if y equals f of x, then I am creating a new function, g of f of x, where g is just the square root sign, and whatever the f of x is, it's going under the square root. So we're thinking about a composition function where the outside function is just the square root symbol, and the inside function is whatever I give you. Okay? So in this case, I'm going to choose my f of x to be a line 2x plus 1. And my g of x function will be the square root of 2x plus 1. So hopefully you can see there's a line. That is my g of x, sorry, f of x, and then this right there is my g of x. You don't need to highlight them. I'm just highlighting them for your sake to visually identify them. Okay, there are some key points that I want you to focus in on. We're going to zoom in to these 2 points. Notice that there's an intersection where we have the point negative 0.5 and 0. What kind of a point is this? When you have a y of 0, what do we call this? An x-intercept. Where is the next point? 0, 1. That is a y-intercept. Okay, so in this case, we have 2 intersections. They happen to be the x and y intercepts. When we are looking at a table of values for f of x, so let's just pretend we have some here. I'm going to write x and 2x plus 1. Let's say that I have 7, negative 7. No, I'm lying. I want to do negative 3, not 7. Negative 3, negative 1, negative 0.5, 0, 1. And let's do positive 3. Okay, so f of x, this is our line. Hopefully we can do this a little bit quickly. 2 times negative 3 plus 1, what would I get? Or you can look at the graph. Negative 3, negative 5. What about negative 1? Almost. Negative 1, yeah. Negative 5 is 0, right? I'm just looking at the graph. At 0, I have 1. At 1, where am I? 3. And at 3, at 7. Okay, now when I go to graph g of x, I am going to take, this is, okay, the long way to do this would be to use the same x values, negative 3, negative 1, negative 0.5, 0, 1, 3, and g of x, remember this is the square root of f of x, meaning the square root of the y values. So rather than calculating this equation from scratch, all I'm going to do is say the square root of negative 5. Nope. D, N, Do you guys remember what that stands for? No? Does not exist. Why not? Because there's a negative in the radical. That's right. Okay. So then at -1, I have square root of -1. Nope. DNE. At -0.5, I have a square root of 0. That gives me 0. At 0, I have the square root of 1. 1. Square root of 3, which is some number. Doesn't matter right now. And square root of 7. We can use our calculators to figure this part out. This is going to be 1.7 something. I don't know. This one is going to be probably 2 point something. I don't know. Doesn't matter. Key things that we can glean from this. When we have a function created by the square root of another function, because we cannot take the square root of a negative number, we need the domain of the square root function such that f of x, the original f of x, has to be greater than 0. Original y values must be positive. Okay, and this is kind of, remember when we did composition, the range from the inside function is the domain of the outside function, but we have an additional restriction because our outside function is a square root. In that, they have to be positive. Okay, so we have to have positive y values coming in from the original function in order to put it under the square root. The other thing that we are going to focus on is notice these two key points. The x values don't actually matter because when I go to square root, I'm more interested in the y values. So I'm going to use this as my star point. Whenever you have an x value with y coordinate 0, or you have an x coordinate with a y value of 1, these are going to be invariant points. Invariant means they're not going to change from the original to the new graph. They're going to intersect these points. Another way to call these are intersections. Intersections. Oops. Intersections. Okay, so when your original graph gives you a y value of 0 or 1, the x value in this case doesn't matter. Whatever coordinate that is, it's going to be the same coordinate when we take the square root of that function because we're taking the square root of the y values, right? So some key points here. Not sure if yours are fuzzy. On the other, in the other class, this chart was a little bit fuzzy, so I'm just going to rewrite the restrictions here. When f of x is less than 0, when f of x equals 0, when f of x is between 0 and 1, when f of x equals to 1, and when f of x is greater than 1. That's what these bits say here. Okay, when I'm referring to f of x, remember f of x is the original function. So when the original function produces negative y values, our new function is undefined. When the original function is equal to 0, y value of 0, we have an intersection point. They're going to cross over because those points are invariant. Same with if we have a y value of 1, that's going to be our next intersection. Now, between those intersections, we have some funny business going on. If the y values are between 0 and 1, so we have a fraction, so 1/2, 3/4, 5/8, something like that, then the square root function is going to be above the original. The y values are going to be bigger in the square root function than they were in the original function. However, once we cross the boundary of 1, the original y values are bigger than 1, that is when we're going to see the square root function cross over, and now it's going to be below the original function. So between the intersections, the square root function is higher. After all the intersections, the square root function is lower. So let's take a visual example of what that is on our next page. So in this chart, we have our x values are here. The x values are the same for both. Here we have f of x equals 4x minus 3. And then we have g of x, which is the square root of f of x. And we can stick this into our calculator. Let's take a look at what do the values look like. I'm going to pull out my calculator here. I'm going to say let me clear that again. 4 times -3 minus 3 gives me -15. Is that right? Oh, sorry, sorry. I was looking here. That's not what I meant to do. My x value is 0. My bad. Sorry about that. Blue pen. Okay, 4 times 0 is 0, minus 3 is -3. The square root of -3 is undefined. They did the first one for us. Apologies for that. I'm going to do the same thing with the rest of them. So 4 times 0.75 minus 3, that's going to give me a y value of 0. The square root of 0 equals 0. Same thing, 0.8 times 4 minus 3 gives me 0.2 on my original graph. Or you can, if you want to, you can write it as a fraction, 1/5. Doesn't matter to me in this case. So the square root of 0.2 is approximately 0.45. Notice my x value is a number between 1 and 0. My original function is 0.2. My square root function is 0.4. So it is higher than the original. All right, and then I'm just going to go through 4 times 1 minus 3, 2 times 4 minus 3, 3 times 4 minus 3, and 4 times 5 minus 3. 1, 5, 9, 15. Okay, 1, 5, 9, 15. Oh, sorry, 17. So now when I look at my square root, I'm going to square root all of these. It's going to give me sometimes ugly numbers and sometimes nice numbers. This is approximately 4.12. This is 3. This is approximately 2.2. This is 1. Okay, let's zoom in on our key points. My key point is when I have a y value of 1 and a y value of 0. Here's one intersection. Here's the other intersection. When I go to graph this, and it's going to be a bit of a messy graph because we have decimals, but bear with me here. So I'm going to do f of x in blue and then g of x in green. 0.0 is -3. 0.75 is at 0. 0.8 is at 0.4, so it's a little bit higher. And then 1, 1, 2, 5, and good enough. There's my line. My hand is a little bit shaky. But this is the graph of f of x. Okay? When I do my green graph, at 0.75, I also have a 0. At 0.45, I have 0.45, so it's a little bit higher. 1, 1 is my intersection. And then 9, nope, 3, 3. So that's my graph of g of x. Okay, I don't have a ruler online, at least not a very good one. But you can see that there's the two intersection points. Maybe I can redraw it while I'm zoomed in. It's a little bit better. Intersection here, intersection here. After x equals 1, the green is below the blue. And between my intersection points, again, I'm just going to zoom in here. You can see that my green function, oops, is on top of the blue function. So between the intersections, the square root is higher. After the intersections, the green function is lower than the original. Okay, also notice the general direction. My blue function is going up and to the right. My g function is also going up and to the right. The basic shape is different, but their directions are the same. Up and to the right. So looking at here, the points of intersection 0.750 and 1, 1. Okay, how are they related? The x-intercepts are related because the x-intercepts have a y equal to 0, which is our invariant point. The definition of invariant we already talked about in our last unit, so I'm just skipping over that one right there. Okay, now for which values of x is the square root function above the regular function? So it's going to be between our x-intercepts, right? Or sorry, between our intersections. So our first intersection is at 7, 5, and our next intersection is at 1. So the x must be between them. So the square root is above the original between the two intersection points, and it is below after 1. When x goes past 1, then the graph of the square root is below the original. Okay, let's take a look at a visual demonstration. Now I'm going to give you a quadratic graph. Okay. We know that a quadratic is a parabola. We know that our invariant points are going to be the x-intercepts, right? So right away, I know that I'm going to have an intersection here and an intersection here. I also know I'm going to have an intersection where I have a y value of 1. How many other intersection points should I have? Y value of 1. How many more intersections should I have? 1 or 2? 2, right? Because we have a parabola that's going up, I'm going to have another intersection somewhere here and somewhere here, where the y value is 1. Okay, so the domain of our function here, the one that's in the picture, is that x can be all real numbers. However, because this is a parabola, it has a minimum value, and it actually shows you what the minimum value is here. Our minimum value is at y equals negative 5.25. The range is what can y be? Anywhere from the vertex up. So that means our range is y must be greater than or equal to 5.25. Now, when we take the square root, we cannot take the square roots where the y values are negative. So we cannot take negative values. That means we can only take the square root of the function wherever the entire function is above 0. So looking at my picture, I cannot use this part of the graph because it's in the negative y value. So I know I'm going to have a key point here and a key point here. I know I'm probably going to have another intersection somewhere up here where I have a 1. So I can say the x-intercepts are going to be, looking at the picture here, negative 2.79 and positive 1.79. Those are going to be the starting points. Now, because I'm not using the bottom half of this graph, what I essentially have is two pieces. One of the pieces is going up and to the right, and the other piece is going up and to the left. So because I have two pieces, I'm going to have two radicals, one going in either direction. So here, my domain for my radical function is going to be looking like this. On the right side of the graph, I'm going to start at the x-intercept, be above the graph, and go off like this, right? If I just cover half the graph and focus on the right side, I know my starting point, I know my intersection, I know I'm going to go up and to the right because that's the original graph. That's what the original graph is doing. So part of my domain is that x will have to be greater than or equal to 1.79. However, I have another piece. So that means on this side, my starting point is the black. I'm going above the graph to the blue, and then I'm following the direction of my graph, up and to the left this time. So the other half of my domain is that x has to be less than or equal to negative 2.79. So my domain ends up being in two pieces because I had to split my graph into two pieces. Anything here is undefined. What's the range of my new graph, the square root graph? What are the allowable y values? Where is my starting point and where am I going? Greater than or equal to 0. Perfect. Okay, so I know my starting point. I know my intersections. Between the intersection, I'm above the graph. The rest of the graph is below the original, but going in the same direction. So I have included the picture of what the square root would look like, which matches all the definitions we have talked about. How are we feeling about this? Okay, for the last example, I'm going to walk you through what I would like you to do, and I want you to work on this page with your partners. Step 1, I want you to draw the graph or draw the equation of f of x in y equals mx plus b form. So look at the picture. What's the equation? Number 2, I want you to identify what are the invariant points. What are the coordinates where y is 0 and 1? I want you to sketch what you think the square root of f of x would look like without doing any points calculation, just looking at the invariant points here. I want you to identify the domain and the range. And once you have done that, I want you to check your work by plotting some points. The points I'd like you to check are these: 3, 2, -1, -6, and choose your own adventure. You choose one more point to test. Okay, so with your partner, identify these 4 things without doing any calculations. Just use observation. Then check your work by doing some calculation and connecting the real dots and see how close your observation analysis is to the calculation analysis. Okay? So take a moment and do that.